We've all seen those incredible demos. AI agents that can write code, book a flight, or even manage a whole sales pipeline. But here's the thing. When we try to move these from a cool demo to a real-world product, a really frustrating pattern starts to show up. We call it the stalled pilot. These big, important projects, they're failing. And it's not because the language models aren't smart enough. No, it's something much more fundamental. It's a deep flaw in their architecture. And what's wild is that it's a problem engineering actually solved about a century ago using a field called control theory. This quote here from the 2025 AI Agent Report, it just gets right to the heart of it. The pilots are failing because they don't have an operating system to manage everything. The LLM itself isn't the problem. And that's our central thesis for today. We're out here building these amazing autonomous systems, but we're completely ignoring the basic laws of cybernetics, the actual science of control. We've basically just been building superpowered chatbots when what we really should have been doing is engineering dynamic systems, systems that you can actually steer, stabilize, and, well, control. So the big question is, how do we fix this? Well, we're going to tackle this in 3 steps. First, we need to diagnose the symptom, what we call the open loop fallacy, which is what's causing so many of these projects to just fall flat. Then we're going to dig into the mechanism behind the fix. And this is the really cool part. It's a solution that's been around for over a century. And finally, we'll put it all together and lay out a practical, stable architecture for building agents that you can actually trust to run in the real world. All right, so let's start by unpacking the core problem. We need to talk about why these agent loops can look so incredibly smart in a demo, but then act so, well, dumb when you let them loose. It all comes down to a trap known as the open loop fallacy. And this is really the main reason why that brilliant demo agent becomes so unpredictable and just plain unreliable in the real world. So what exactly is open loop control? Well, think about a super simple coffee machine. The kind that just blindly follows a recipe. It grinds the beans for exactly 15 seconds, it heats the water to exactly 92 degrees, and it pours for 30 seconds. It's just executing a pre-programmed sequence. But here's the key. It never, ever tastes the coffee to see if it actually turned out well. And that's the critical flaw. There's no feedback. The system just assumes that its actions created the desired result, and that is a seriously dangerous assumption to make in any environment that changes. And this is where we see a huge mismatch between that open loop design and the messy, chaotic reality that agents have to operate in. Open loop systems are just incredibly rigid and brittle. If an API endpoint changes or a website layout gets updated, the whole plan just breaks. A closed loop system, on the other hand, is completely different. It works in a circle, a feedback loop. It takes an action, then it senses the result of that action, it compares that result to its goal, and then it intelligently corrects its next move. It's adaptive, it's robust, and it's all because it's using feedback. So when we look at actual projects, this open loop fallacy manifests in 3 really common traps. First, there's what we call dumb RAG. Now, RAG stands for Retrieval Augmented Generation, but in this context, it just means flooding the agent's context window with tons of data, basically hoping the LLM will magically stumble upon the right info. There's no feedback loop to check if the data is even relevant. Second, you have brittle connectors. These are those fragile API integrations that just shatter the second a system they depend on gets an update. And third, there's something called the polling tax. This is where the agent has no event-driven way to know when something changes, so it just wastes tons of energy and resources constantly asking, is it done yet? Is it done yet? How about now? And the end result of falling into these traps is, well, it's profound system instability. You get one of 2 things happening. You either get oscillation, which is when an agent gets completely stuck in an infinite loop, just unable to make any real progress, or you get divergence, where one tiny error snowballs and cascades into a massive hallucination. The perfect example is a code editing agent. It finds a bug, it tries to fix it, but its fix actually creates a new bug. And because it can't sense the consequences of its own actions, because that feedback loop is missing, it just gets trapped in this destructive cycle, bouncing back and forth between broken states. So that's the problem. How do we solve it? This brings us to the mechanism for the solution. And what I find so fascinating is that the answer isn't buried in the latest AI research paper. It actually comes from a discipline that's been around for ages, one that predates the first digital computer by decades, and that's control theory, the field of engineering that is literally all about making complex dynamic systems stable and predictable. At its core, the closed-loop mantra is this simple, elegant, and just incredibly powerful cycle. It's 3 steps. First, you perceive. You sense the current state of your environment. What's happening right now? Second, You compare. You measure the difference, the error, between that current state and where you want to be, your goal state. And third, you correct. You take a specific action designed to reduce that error. And this isn't a one-time thing. It's a continuous, never-ending loop that lets a system dynamically steer itself right toward a target. Now, the most famous, most widely used example of this whole principle is something called a PID controller. That's P for proportional, I for integral, and D for derivative. And even if you've never heard of it, I guarantee it runs your world. It's in the thermostat on your wall, it's in the cruise control in your car. PID controllers are basically the unsung heroes that keep all of these dynamic systems stable. And this is where it gets really, really interesting because we can take these battle-tested concepts from 100 years ago and apply them directly to the most cutting-edge AI agents today. Okay, so let's break that down. First up is P for proportional. This part just answers one simple question. How far away from the goal are we right now? Think about your car's cruise control. If you set it to 65 miles per hour, but you're currently going 50, well, that's a big error. So the proportional component takes a big, strong action. It slams on the accelerator. But if you're going 64, the error is tiny, so the correction is just a gentle little tap. It's the immediate proportional reaction to the current size of the error. Okay, next up is I for integral. This is the component that has a memory. It asks, what has the error been like over time? Let's go back to the car. Imagine you're driving up a long, steep hill. The proportional control might give it a good push, but the constant drag from gravity might mean you're always stuck going just a little bit slower than your target. The integral term is what notices this. It sees that persistent error, it adds it up over time, and it says, hey, we need a little more juice here, and it adds just enough power to get you over the hump. It's what gets rid of that slow, steady drift. And last but not least, we have D for derivative. This is the predictive part, the component that looks into the future. It asks, how fast is the error changing? So as your car is accelerating and getting close to that target speed of 65, the derivative component sees that the gap is closing very, very quickly. It anticipates that if it keeps the accelerator floored, it's going to blow right past the target. So it acts preemptively, easing off the gas just a bit to make sure you have a nice smooth landing right at your goal without overshooting. Okay, so this is where the theory really hits the road. Let's see how cleanly these old school engineering ideas map onto the very modern problems we face with LLM agents. For the proportional term, the question for the agent is how far off is the current output? And we can actually measure this using something like embedding distance, which is basically a fancy way of calculating how close in meaning the agent's work is to our goal. For the integral term, we ask, how long has this agent been stuck on this step? This is our escape hatch for infinite loops. And for the derivative term, we ask, is the agent getting closer to the goal or further away? This is what allows us to dampen oscillations and prevent the agent from wildly overcorrecting. Okay, so now that we have this powerful theory in our back pocket, how do we actually go about building a practical, stable architecture? How do we build agents we can truly trust in a production environment? Well, it all begins with a pretty fundamental shift in our design philosophy. This new philosophy really comes down to three core principles. First, we have to kill the idea of the universal agent. Forget about building one single, monolithic agent that does everything. Instead, we build a team of smaller, specialized agents. Second, we need to embrace bounded control loops. This means each of those specialized agents has one narrow, specific, and most importantly, measurable job to do. And third, and this is probably the most important principle of all, we have to separate the doing from the watching. The part of the system that takes action needs to be architecturally separate from the system that observes its performance. A really brilliant way to think about this is using a classic software design called the observer pattern. In this setup, you have two parts. You have the doer, which is our unpredictable, non-deterministic LLM agent. It goes off and tries to do a task. Then you have the watcher, which is a completely separate piece of simple, reliable, deterministic code. The watcher's only job is to monitor what the doer is doing, measure its output against the goal, calculate the error, and then feed that information back to the agent for its next attempt. This is how you create that robust, stable control loop that was completely missing before. And when you start building your systems this way, you end up creating what that 2025 agent report called an agent-native integration layer. Really, you can just think of it as a lightweight operating system for the LLM. This becomes the essential infrastructure that was missing from all those failed pilots. It's what manages state, it's what provides the sensory feedback, it governs what the agent is and isn't allowed to do, and most importantly, it's what closes the loop and finally gives us true control. You know, once you adopt this kind of architecture, it forces a really profound and, honestly, a necessary shift in how you even measure success. In the old paradigm, the one we basically inherited from chatbots, the focus was all on task accuracy. The big question was, did the agent get the right answer this one time? And our main tool was prompt engineering. But in this new paradigm, the one for building real, reliable systems, the focus shifts completely to system stability. Now the question is, does the agent reliably and consistently approach the goal over time? And our method is no longer just tweaking prompts, it's designing and refining system architecture. So let's get really specific about what that looks like. Instead of just measuring accuracy on a single attempt, we start measuring something called convergence rate. How quickly is the agent actually reducing its error over time? Instead of a simple pass/fail success rate, we measure settling time. How long does it take for the agent to not just reach the goal, but to stabilize there? And instead of just counting the percentage of hallucinations, we measure overshoot. How far does the agent go past the ideal solution before it manages to correct itself? You see, these are the metrics of control systems. It's time to stop measuring these agents like they're just fancy chatbots and start measuring them like the dynamic systems they actually are. And this ultimately brings us to a new and I think a much more productive question to be asking. For years now, the entire race has been about building the most intelligent model possible. But what we're learning is that for building reliable autonomous systems, raw intelligence just isn't enough. The goal isn't just to build agents that are correct once in a while. The goal is to build systems that are fundamentally stable. So the critical question we all need to start asking ourselves is no longer how intelligent is the model, it's how controllable is the system we've built around